Good morning. I am Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today, I will be discussing about another topic of Module 3, which is corrosion. And this topic is broadly classified into what are the causes of corrosion, what are its different types, and what are the effects of corrosion and how we can prevent corrosion. Now, coming first to the definition of corrosion. Corrosion may be defined as the destruction of a metal or an alloy because of either chemical or electrochemical reaction which a metal can undergo with its surrounding or in a medium. And this process is the deterioration process, and there is consequently loss of solid metallic material through an unwanted chemical or electrochemical attack by its environment, starting at its surface, and this process is known as corrosion. So, the deterioration of the metallic surface is generally termed as corrosion, and this corrosion process, it is a reverse of extraction of metals. Extraction of metals, when the metal is extracted from its ore and converted to its purified form. So, this corrosion process is the reverse of a pure metal getting converted back into a combined form. Now, how we can say that the process is reverse of metallurgy, or here any metal which is present in the earth or in the mines, we extract suppose we are extracting the iron metal, then iron is not present in the free state. In the ore, the metal is present in the combined form. So, iron in its ore, it is present in the form of either oxide or sulfide. But when we take out this metal from the ore, we are going to do the extraction of the metal, we are going to reduce it, refine, then we are going to roll, and finally we are going to give it shape, different shapes to the metal. Here in the ore form, our metal, it is in the combined form, suppose Fe2O3, but when it undergoes extraction, we convert it into its pure form, that is iron. So, here you can see the iron, it is present in the +3 oxidation state, but here after doing the extraction, our iron is getting converted into the 0 oxidation state in the pure form. So, we can say any metal which is present in the nature in its natural form, that form is the most stable form. But on doing the metallurgy, we are converting the metal into another form, and that pure form of metal is not the stable form of the metal. So, here the metal becomes thermodynamically unstable, and to attain stability, it undergoes reaction and form the product, and this reaction is nothing but corrosion. We see that reaction in the form of corrosion, and the product that is being formed is the corrosion product, and this corrosion product again is going to be thermodynamically stable. Therefore, except for the noble metals, other metals which have high reactivity, they react with either oxygen or moisture which is present in the environment to get back to their more stable form, and generally that more stable form, getting converted into the more stable form, is nothing but corrosion. Now, formation of rust on the surface of iron. or formation of green film on the surface of copper. The responsible factors for the corrosion of a metal are the metal itself, the environmental chemicals, the temperature and the design. So, these are the main factors which support corrosion. Now, coming to the different theories of corrosion. Corrosion is classified broadly into two categories. First is dry or chemical corrosion, and second it is galvanic or electrochemical or wet corrosion. Now, this dry corrosion, as the name suggests, it necessarily takes place in the absence of moisture, whereas the galvanic or the electrochemical or the wet corrosion, it takes place in moist conditions. And because small circuited galvanic cells are being formed, formation of cathode and anode takes place. Therefore, this corrosion is also known as galvanic corrosion. Now, coming first to the chemical theory of corrosion, where the metal directly reacts with the gases present in the atmosphere. So, under the chemical theory of corrosion, corrosion on the surface of the metal is because of the direct reaction of atmospheric gases like oxygen, like halogens, like oxides of sulfur, like oxides of nitrogen, then H2S gas and fumes of chemicals with metals. And the extent of corrosion in this case depends on the chemical affinity of the metal and the reactive gases. The main reaction of metal that takes place here is with oxygen. So, we can say oxygen is mainly responsible for the corrosion of most metallic substances when compared to the other gases or the chemicals. Now, coming to the types of dry corrosion, there are three main types of dry corrosion. The first is the oxidation corrosion, where the metal undergoes reaction with oxygen. So, here you can see I am showing a reaction where a metal undergoes oxidation to produce metallic ions and corresponding number of electrons are being released. These electrons, they are accepted by the oxygen to form O minus, and the overall reaction will be the metal going to react with oxygen to form metal oxides. So, different metal oxides are being formed. I have taken this reaction specifically for the alkali metals. Now, what we can say that there are certain metals which directly react with oxygen in the absence of moisture. Generally, oxidation corrosion does not take place at low temperatures, but alkali and alkaline earths, even at room temperature, they have the tendency to react with oxygen. So, alkali and alkaline earth metals, they react with oxygen at low temperatures also and form corresponding oxides, while some metals, they react with oxygen at higher temperature. And there are certain metals like silver, gold and platinum, they are not going to get oxidized as they are noble metals. Now, here I am showing the reaction how the two ions they diffuse towards each other. Here the metal ions and oxygen, they combine to form metal oxide. Metal can combine with OH minus to form metal hydroxide. Metallic ions, they are reacting, and here the pure metal can react with O2 minus to form the metal oxide. So, the metals, they react with atmospheric oxygen in these three different manners. Either they can first get converted into the metallic ions and then react, or the metal, it can react with the oxygen itself. Now, during the process that I was explaining, during this oxidation process, a thin film of oxide is formed on the surface of the metal, which protects the metal from further corrosion. But if diffusion of either oxygen or metal is across this layer, if either of the two can cross the layer, then further corrosion is possible. Here I was discussing the metal oxide layer is being formed. Now this layer is generally protective towards the metal, but even if after formation of this metal oxide layer the diffusion of oxygen or metal does not stop, then corrosion will take place again and again, and further layers will get converted into the metallic oxide. So that means this metal oxide layer which is being formed, it plays an important role in the process of corrosion. How? I am going to discuss. Now there are different types of oxide films that are going to be formed on the surface of the metal, and this oxide film will decide whether further corrosion will take place or not. So the different types of oxide films I am taking. First is the stable film. Here oxides of lead, aluminium and tin, when oxygen reacts with this metal, they form metal oxides, and this metal oxide layer is stable. It is stable and the layer is tightly adhering to the metallic surface. Suppose this is the metal surface, the oxide film that is being formed is tightly adhering to the surface of the metal. Now this stable oxide film will inhibit further corrosion because it forms a barrier between the pure metal and the atmospheric oxygen. So the pure metal is not exposed directly now to the atmosphere. Therefore this metal oxide layer is going to protect the metal. Second type of layer is the porous layer. Here there are small pores which are present in the oxide film. So in the case of porous oxide film, the atmospheric gases, they can pass through these small pores and they can react with the metal, and the corrosion will continue till the entire metal is getting converted to its oxide. And such type of oxide film is being formed by alkali and alkaline earth metals. Now in this case the porous film, suppose this is the surface of the metal and a porous film is being formed. There are gaps in between the film, so the atmospheric oxygen can pass through these pores and can corrode the inner layers of the metal ion. The third layer that is being formed is the unstable. Silver, gold and platinum, they form the unstable oxide layer. That means as soon as they are going to react with oxygen, they are going to form an oxide layer, and that oxide layer will as soon decomposes back to give you metal and oxygen. And we say that these metals generally do not undergo oxidation corrosion. So in this case, because of the unstable oxide film that is being formed, this type of film prevents the further corrosion. So this is a reversible reaction between metal and oxide. Metal oxide is being formed, and as soon as this metal oxide forms, it breaks down to give you pure metal and oxygen. So here it is oxygen. Next is the volatile layer. As the name suggests, as soon as the oxide layer is formed, it volatilizes and the new metal layer is being exposed for the further corrosion. So, in this case continuous corrosion takes place and this corrosion is rapid. So, and corrosion will continue till the entire metal gets converted into its oxide layer. So, one example is molybdenum. Molybdenum, it forms a volatile oxide film of molybdenum oxide which accelerates corrosion. So, there are the 4 different types of layers and depending upon which layer is being formed on the metal, that layer will decide whether further oxidation will take place or not. Now, coming to the Pilling-Wedworth rule. Now, this rule, it states that an oxide layer which is being formed, it is protected or a non-porous film is formed if the volume of the oxide, if this is the volume of the metal, then the volume of the oxide is as grand as the volume of the metal from which it is being formed. So, Pilling-Wedworth rule says that an oxide layer is going to be protective in nature only when this, if this is the volume of the metal, then the volume of the oxide is at least as large or as grand as the volume of the metal. And if the volume of the oxide is less than the volume of the metal from which the oxide layer is being formed, then it is going to result in the non-continuous oxide film or the porous film, and as a result this type of layer is going to be non-protective and it will not prevent the access of oxygen to the fresh metal surface below. So, in the case of aluminium, the oxide film is being protective because the volume of the oxide is as large as the volume of the metal aluminium. But in the case of alkali and alkaline earths, here their oxide film is not protective because the volume of the oxide film is less than the volume of the metals. As a result, the film is going to face stress, thereby it will develop cracks and pores in its structure and thus the corrosion continues. So, I have already taken that aluminium oxide, here the volume is high and because of the absence of any pores, the rate of oxidation, it nearly decreases to 0. Now, the second type of dry corrosion is due to the other gases such as Cl2, chlorine, sulfur dioxide, H2S, NOx. So, in dry atmosphere, these gases can react with the metal and they can form the corrosion products, which may be protective or they may be non-protective. Again, because of their chemical affinity, only those reactions will take place where the metals, they are going to react with each other. So, here the corrosion products are going to decide whether the layer will be protective or it is going to be non-protective. For example, if dry chlorine reacts with silver, then it forms a AgCl layer which is protective, whereas tin chloride layer is volatile and hence unprotective in nature. In petroleum industries, at high temperatures, H2S attacks steel, forming iron sulfide scale which is porous and it interferes with the normal operations. And the third type is by the liquid metal corrosion. In different industries, molten metal passes through metallic pipes and causes corrosion due to the dissolution or due to internal penetration. For example, liquid metal mercury, it dissolves most metals by forming amalgams and thereby corroding them. So, these are the three different types of dry corrosion. Next, coming to wet or electrochemical theory of corrosion. Now, this type of corrosion necessarily takes place in the moist conditions, and this type of corrosion, it occurs when the metal, it comes in contact with a conducting liquid, or when two dissimilar metals, they are immersed or dipped partly or partially in a solution. Now, according to this theory, there is the formation of a galvanic cell on the surface of the metal. So, small short circuited galvanic cells are formed. Some parts of the metal surface, they act as anode, whereas the rest part, it acts as cathode. So, the chemical in the environment and humidity, it acts as an electrolyte. Oxidation generally or necessarily it takes place at the anodic part, and it results in the corrosion at anode. So, wherever oxidation is going of metal will take place, the corrosion will take place at that part. That means corrosion will take place at the anode, whereas reduction takes place at the cathode. The corrosion product is formed on the surface of the metal between anode and cathode. So, the ions are going to be released and the corrosion product, it is going to be formed somewhere between the anode and the cathode. Now, coming to the mechanism of electrochemical or wet corrosion. Now, the electrochemical corrosion, it necessarily involves formation of separate anodic and cathodic areas between which the current flows through the conducting medium. Occurrence of oxidation or corrosion is going to take place at the anode or the anodic areas, which are going to generate metallic ions. So, metallic ions are going to be formed at the anode, and non-metallic ions like hydroxide or O2 minus, they are going to be formed at the cathodic areas. And these ions, metallic ions and non-metallic ions, they are going to diffuse towards each other through the conducting medium and forming the corrosion product somewhere between anodic and cathodic areas. So, if this region is the anode and this region is the cathode, it will release metallic ions, it will release non-metallic ions, and these ions are going to move towards each other and they are going to form the corrosion product somewhere between the anode and the cathode. Here I am showing an example of electrochemical cell. Zinc dipped inside zinc chloride solution, copper electrode dipped inside copper chloride solution, and the left electrode, here the zinc undergoes oxidation. So, the zinc is going to behave as the anode and the copper undergoes reduction, therefore, it is going to behave as cathode. If we say which is going to undergo corrosion, obviously this zinc, it is going to behave as anode. So, the corrosion will take place of the zinc metal, whereas our copper metal is going to be protected, it will not undergo corrosion. Now, by taking the example of rusting of iron, the reaction can be explained that it may occur in two ways. If I am concentrating on iron, then the rusting of iron which is taking place on the surface in moist conditions, then this reaction can take place in two ways. The first is the evolution of hydrogen, and the second is the absorption of oxygen. So, electrochemical corrosion can take place in two ways, either by evolution of hydrogen or by absorption of oxygen. Now, coming first to the evolution of hydrogen. Now, evolution of hydrogen generally takes place in the absence of oxygen, and at anode we know that oxidation is going to take place. So, here the metal, it will undergo oxidation to produce metallic ions and release equivalent amount of electrons. And since these hydrogen ions, they are formed due to the acidic environment, and the reaction that is going to take place in acidic environment and in the absence of oxygen will be, these hydrogen ions, they are going to accept the electrons from the anode and release hydrogen gas. So, this is the reduction reaction, and the overall reaction will be iron reacts with hydrogen ions to form ferrous ions and release hydrogen gas. But this reaction is going to remain same. Anodic reaction will remain same, but the cathodic reaction will change according to the medium. This reaction is taking place in the acidic medium, but if our medium is neutral or alkaline and there is absence of oxygen, then the reaction that is going to take place at the cathode will be the water, moisture, because this reaction is taking place under moist conditions. So, the moisture or water is going to accept the electrons released by the iron to form H2 plus 2 OH minus. So, here again the H2 gas is being released in the atmosphere. Now, and these two OH minus which are being formed, they react with ferrous ions to form ferrous hydroxide, which ultimately forms ferric hydroxide. So, these are the two reactions that are going to take place in the absence of oxygen. Here, in this case I am showing how the metal react in the acidic environment and it is dissolved to release the H2 gas. All metals above hydrogen in electrochemical series can show this type of corrosion. In hydrogen evolution of corrosion, anodic area, that is the metallic area which is being dissolved, is large as compared to its cathodic areas. So, here I am showing how the metal getting dissolution of the metal takes place to form ferrous ion and release of electrons, and these electrons, they are intercepted by the 2H plus to form hydrogen gas. Sorry, there are large anodic areas and there is small cathodic area. Next reaction that can take place is by the absorption of oxygen. Now, in this case, it is going to take place in the presence of moisture as well as oxygen, and this type of corrosion takes place in neutral or basic medium in the presence of oxygen. The oxide of iron covers the surface of the iron, and the small scratch on the surface creates small anodic area, and the rest of the surface, it is going to act as cathodic area. So, here again anodic reaction is same, which is the dissolution of the metal, that is the oxidation occurs. So, iron is going to release Fe plus 2 electrons, and in neutral alkaline medium, here oxygen in the presence of moisture, it is going to accept the 2 electrons to form 2 OH minus. So, here the reduction is taking place and this is going to be the overall reaction, and the same process can take place in the acidic medium. If there is acidic conditions and oxygen is also present, then the H plus, they are going to react with oxygen and they are going to accept the electrons to form 2 water. So, these are the different types of reactions that can take place during corrosion. So, here cathodic areas are large and anodic areas are small. Here I am showing the corrosion in the aqueous neutral solution of the electrolyte. So, here again Fe is getting converted into Fe plus 2 electrons, and here the oxygen will react with water and it is going to accept the electrons to form hydroxide ions. Finally, the ferrous ions, they are going to react with hydroxide ions to form ferrous hydroxide, which is going to then release or get converted into ferric hydroxide. Now, ferric hydroxide which is being formed, it is actually hydrated ferric oxide, Fe2O3 H2O, which is a yellowish colored rust, and anhydrous magnetite Fe3O4, which is a mixture of FeO and Fe2O3. It is also being formed, which is brown to black in color. Now, it is markable that the corrosion occurs at the anode. Corrosion, dissolution of the metal takes place at the anode, but the corrosion product is formed near cathode. Why? Because diffusion of iron is faster as compared to diffusion of hydroxide ions. So, when both the ions are moving towards each other, ferrous ions, they move fastly and there is slow movement of the hydroxide ions. So, the corrosion product that is being formed between cathode and anode, it is formed somewhere towards the cathode. Now, coming to the differences between dry and wet corrosion. Now, the corrosion, dry corrosion, it takes place in the absence of moisture, whereas the wet corrosion, it takes place in the presence of a conducting medium. Now, the dry corrosion, it involves the direct attack of chemicals on the metal surface, whereas in the wet corrosion, it involves the formation of electrochemical cells. Dry corrosion is a slow process, whereas electrochemical corrosion is a fast or the rapid process. Now, the corrosion products, they are formed at the site of corrosion. Where corrosion is taking place, at that point only the product are going to be formed. But here in the wet corrosion, the corrosion occurs at the anode, but the corrosion products, they get deposited near the cathode. Dry corrosion, the process of corrosion is going to be uniform, but in the wet or electrochemical corrosions, it is going to depend upon the anodic part of the metal. If the anodic part is larger, cathode is smaller, then that cathode is going to require small number of electrons, therefore corrosion rate will be lesser. But if anode is smaller and cathode is larger, then the cathode, for its sustainability as the metal only, it is going to require large number of electrons, and that electrons are going to be supplied by the anode, therefore fast corrosion is going to take place. Now, there are several types of corrosion: galvanic corrosion, pitting corrosion, stress, crevice, erosion corrosion, soil corrosion, microbiological corrosion, waterline corrosion, differential aeration corrosion and intergranular corrosion. Depending upon the different conditions, there are different corrosions. Coming first to the galvanic corrosion, which is also known as bimetallic corrosion. Now, what happens if we keep two different metals in contact with each other and they are jointly exposed to the corrosive environment? Then the metal which is higher in the electrochemical series, it will undergo corrosion because it has a tendency for oxidation, and oxidation in the case of corrosion necessarily takes place at the anode. So, here when two dissimilar metals are connected and they are exposed to an electrolyte, they will form a galvanic cell. The anodic metal will be oxidized and it will undergo corrosion. Zinc and copper metals connected with each other in an electrolyte medium, they form a galvanic cell, where zinc is going to act as anode and it will undergo corrosion, whereas cathode will be formed by the copper and it will going to remain unaffected. So, here if we keep these two metals in contact with each other, they are going to undergo galvanic corrosion. Zinc will undergo oxidation, whereas the electrons released by the zinc are going to move towards the copper, which are going, and the copper will undergo the reduction reaction. So, corrosion will concentrate at the zinc metal. These are the different reactions which are taking place. How zinc undergoes oxidation or the corrosion, and the copper, it accepts the electron and it undergoes reduction and it will be unaffected by corrosion process. Now, this galvanic corrosion, it can be avoided by coupling metals close to the electrochemical series. We should not form a couple between the different metals, or we can fix the insulating material between the two metals, and we can use larger anodic metal and smaller cathodic metal, so such that the requirement of electrons is less. And the examples of galvanic corrosion, they are steel screws in the brass marine hardware, steel pipes which are connected to copper plumbing, steel propeller shaft in bronze bearing, zinc coating on mild steel, and lead tin solder around copper wires. Thank you.